Welcome back, everybody. This is Chemistry 2330, Introduction to Organic Chemistry, here on week 9 of our 2020 fall semester here. So hopefully all of you had a nice, safe weekend, maybe got some rest, maybe got some work done. We'll see. I personally was out in the garden, got to clean my entire workshop. It was 4 hours of bliss for me. I don't know, I have a woodworking shop and it was just wonderful. So I really enjoyed myself. I hope all of you had at least an opportunity to do something enjoyable over the weekend, as long as you were wearing a mask. So there you go. Anyway, all right. So are there any questions before we begin, before I start with the administration stuff?
Dr. Irving?
Yes.
This probably is redundant, but that last lecture, you did get a chance to post that, correct?
It should have posted this morning because
Okay.
My computer glitched out and actually shut itself off and rebooted itself. So, but
Okay.
I think it is posted now. Let me double check. Channel videos, close, update. Yes, the number 8, Zoom 8, lecture 2. Yes, it is posted.
Okay. Thank you so much, sir. I appreciate that.
Let me see if that's the right day. That may be. If not, I'll double check and after this.
Yes,
But
sir.
for this week, we're going to finish up chapter 11, which is spectroscopy. We have 3 components of spectroscopy: IR spectroscopy, what we call proton NMR or hydrogen spectroscopy, and carbon spectroscopy. And so we're going to look at all 3 of those and how they compare and contrast and do different things, but tell us a lot about the molecular structure. After this week, we're going to finish up chapter 11 on Wednesday. We'll have a review on the 26th, which is next Monday. And then we have our next exam number 2, on October 28th. It'll be a proctorio, a proctored exam. It'll be during regular class time, and it'll be about the same number of questions, a little weighted toward chapters 8 through 11, okay? Because we did chapters 1 through 6 on the first one, it's going to be a little more weighted 8 through 11. However, there will be information from the previous chapters there. So don't just study that, just reinforce it, okay? In addition to that, due this week, the full videos for this are also posted on YouTube under the Introduction to Organic Chemistry channel. Again, I'm doing the goals for this because I want to draw your attention to certain things, and this particular chapter works really well with the goals function, okay? We'll have homework for 9 and 11 will both be due on Friday at midnight on the 23rd of October. And then we'll, of course, come back on Monday, do our review, and get our heads straight for our exam on the following Wednesday. Okay. Questions about administration right now? Okay. So your group A people are online. You want to make sure you go to your group A labs on Friday. Group B people are live. There's only one group B left, so that's live today. And then group C, or the online only section, of course, your lab starts on Friday as well. So don't forget those. You should have got a different set of emails this week than previously. The other thing I want to remind you in the lab is this is makeup week. If you've missed an assignment, a pre-lab or a post-lab, please go ahead and do those things and upload them to the correct section and group. And by Wednesday at midnight, we're also going to open up on Wednesday from noon to 6 quizzes that might have been missed that are online. Okay, if you missed an online quiz, you can take an online quiz. The live quizzes you cannot take, but the online quizzes you can. So that allows you to make up any work you have by this Wednesday, and then we're going to get all of that. The AIs and I are going to get together and make sure everybody's grades are right, and then we'll start posting, what things are missing, and we should have a fairly good idea of what your grade is at that point, because all of the mixes and matches and group changes, I think we've kind of narrowed down and kind of figured out now. So I think we'll have a really good thing. But so I want you to check next Monday your grade in lab. And then if something's missing, go ahead and ping me and or your AI. Okay. So that being said, any more questions? Okay, got somebody in the waiting room. I'll let them in while I'm doing that. Okay, what I'm going to do is I'm going to share my screen and we're going to talk a little bit about goal 1, but then I want to actually talk about goal 2 for the bulk of today. Okay, let's see if it's going to be good to me today. I rebooted all my internet stuff, and so it should all be working, and I was able to hear people, so that's great. Okay, so when we talked last time, I talked about how we were using parts of the electromagnetic spectrum to learn things about chemical compounds. And the first thing we did was we talked about this one little section here that was infrared spectroscopy. And infrared spectroscopy particularly was able to be absorbed by different types of bonds. And when it was absorbed by different types of bonds, that would be removing it from the light we had. And so when we did this, we saw that different functional groups showed up in different places based on energy, okay? So we noticed that our light and heavy atoms right here were the highest energy, okay? Followed by our triple bonds, our double bonds, and our single bonds, okay? So the thing to note here is that any individual band does not tell you the exact functional group. However, each absorption band tells you a part of that. For example, if we had an aldehyde, we would see a peak here for the CO, but then we'd see a peak up here for the CH, okay? And if we had an ether, we would only see maybe some carbon and hydrogens here and nothing else till down here. So when we look at the functional group, you have to look at all the different types of bonds in the entire molecule and know where they're going to show up based on their energy. Okay, so that's the thing I wanted to drive home here. You're not going to look for one bond and say, oh, it's obviously this. Okay, the molecule has that bond in it, but there might be other bonds in there. So don't just stop at one peak. Go ahead and assign all the different peaks, and you'll know all those different types of bonds are in that compound. Okay. So that being said, let me go. No, not that button. This button. There we go. Let's go back to this electromagnetic spectrum right here. And in that electromagnetic spectrum, we have these really, really long wave right here. Okay. So this right here frequency interacts with bonds that can absorb or make them vibrate out of heat. We have a band here that actually also will absorb energy and excite an electron. And so these are things where you have things that glow in the dark or have a fluoresce under black light. You're going to see stuff absorbing in that region. But today we're going to talk about NMR, or nuclear magnetic resonance. And so what we're going to do is we're actually going to hit the nucleus of atoms with these very long radio waves. And what we're going to do is that magnetic component of that long radio wave is going to interact with the nucleus of the atom. Okay, so that's the difference. We're still using this electromagnetic spectrum here, but we're looking for a different thing. So in our nuclear magnetic spectroscopy, we're going to start with the simplest version, which is hydrogen NMR. And we call it proton NMR because when we think about hydrogen, it has many isotopes possible. And the particular isotope we're dealing with is one proton, one electron, and that's it. No neutrons in that. So this is the exact molecule we're doing. That's why we call it proton NMR, or we call it 1H. That 1 stands for which isomer it is, isotope it is. So this is saying that it has a molecular mass of 1 atomic mass unit. Now in 13, when we see carbon 13, that means that we have an isotope of carbon that has the atomic mass of 13. We'll talk about that next. Okay, so when we talk about this nuclear magnetic spectroscopy, we're actually talking about hitting the nucleus of an atom with radio waves and then waiting to see how long it takes for it to come back into alignment. And that's all we're doing. So we're basically, imagine you have a whole bunch of spaghetti noodles all lined up together in a box, and you throw them up into the air, and they're all over the place. And then how long does it take for them to come back and for you to get them all lined up again and put back in that box? That time domain is what we're talking about. Okay, so let's talk about why. Okay, so when you have a nucleus of an atom, the protons and the neutrons each have what we call half spin. Remember when we were doing electrons, and electron had a half spin up, half spin down, and they had to spin pair? Well, the same kind of thing, not exactly the same, but the same kind of thing happens in the nucleus. And it happens to align with magnetic fields. So if you have an odd number of particles in your nucleus, like an odd molecular weight, chances are you're going to have a mismatch between a plus and a minus, and you're able to see that because you have half a spin that's unparalleled. So let's look at what we have here. So if we don't have a magnetic field in the system, the spin of the nucleus, just like a planet has, if it spins on its axis, it has a magnetic field associated with it, right? Well, the particles inside the nucleus also have this, and therefore the entire nucleus has this magnetic field on it. And in normal time, like in a solution or something, they're just all randomly associated wherever they want to be. Okay, if you put in a big, huge magnetic field, they have to align with it. They have to either be north-south with it or south-north with it, and therefore they all align. Now, if you have equal numbers of them, of spins, they'll cancel out. So you have to have an odd number of spins. And when you have an odd number of spins, that's something that you can look for when you pulse it with electromagnetic radiation. Okay. Both hydrogen and carbon have an odd molecular weight, meaning that they have a mismatch between protons and carbons in their nucleus, which allows them to have spin. Okay. So the idea here is that when we absorb the electromagnetic radiation, those radio waves, what it does is it flips some of the nuclei from that lower energy state to that higher energy state. Okay, because we've given it energy from that nuclear magnetic rate, from the radio wave, right? So it'll flip it into a higher energy state. Okay, now, well, it's still aligned in the magnetic field. It's not very happy. It would rather lose energy and go to its lowest energy state. So at a certain amount of time, it's going to flip back. And so what we're looking for in an NMR is when these flip back, it gives us a signal. And notice it's a time-based thing. So we pulse it, and some of them flip up, and then we wait until we see them flipping back. And the speed at which they flip back has everything to do with the electrons around the nucleus, making it shielded or not shielded. Basically, if you have a lot of electron density around their nucleus, it takes longer for it to realign with the magnetic field. If you don't have very many electrons around your nucleus, it does it faster because the electrons can't shield it from that magnetic field that's there. Okay. So, what does this mean? This means that all the electrons create their own little magnetic fields, and when they get into this alignment, those little electrons are the part that will shield the nucleus from the magnetic field. So imagine the electrons having their own spin and poles, and the more electrons you have around it, the more it shields the inside. And therefore we call that shielding. Okay. Now, in most NMR, because we're using big, huge ranges of frequencies, we tend to use a reference compound for both proton and carbon NMR. And the one we use is called Tetramethyl Silane. And it turns out, because of this sulfur here, it changes the time it takes for these, both the hydrogens and the carbons to relax. And it tends to be, tends to make them relax the fastest. So we tend to call that 0 in all of our spectrums so that we know that, everything's going to happen after this compound relaxes. Okay, so what does the machine kind of look like? Well, you have a powerful magnet. Most of the time now, we have superconducting magnets, which means it looks like a giant thermos with a tube running through the middle of it. And inside of the thermos is liquid helium at 4 degrees Kelvin. That's minus 294 degrees Celsius. And then outside of that is a liquid nitrogen door, which is at minus 120 to keep the 4 Kelvin cold as long as possible. We need this cold temperature to create this huge magnetic field. Okay. Now, once you have that huge magnetic field, you put your sample inside it, right here. And your sample is in solution, and so that all the spins are random. And you actually spin the tube to make it as homogeneous as possible. So all the spins basically are canceling each other out, and so you basically see nothing. So if you pulse it, you'd see nothing, okay? Now, when you have it in that magnetic field, they're now all aligned. And whenever they can pair up and cancel each other out, we don't see those. But when you can't cancel out, those are the ones we're looking for. Now, the next thing we do is we hit it with radio frequencies, okay? When we hit it with that radio frequency, some of them, not all of them, some of them flip over. And then slowly, one by one, they're going to come back and realign based on how much they're being shielded by those electrons. So if there's no shielding, it's going to flip back really quickly. If there's a lot of shielding, it's going to flip back a lot, very, very slowly. Okay, so that's kind of how the thing works. But so what do we need to know for this class? Well, what we need to know is the things that are important to proton NMR. We have 4 things that we will see in every single proton NMR spectrum or hydrogen spectrum, okay? The 4 things we look for are the number of signals. That tells you different types of hydrogens. We'll talk about that in a minute. The intensity of the signals. Because the hydrogen is so common, we have a lot of it there, and therefore we can actually take a look and integrate the area under the curve, and we know exactly how many hydrogens we have. So we have number of signals based on how many different types of hydrogen you have. The intensity of the signals tells you how many of that type of hydrogen you have in that peak. Okay. The next thing we look at is position. I said, remember, some of them go faster and some of them go slower. So we have a scale from 0, which is where our tetramethyl silane is, moving outward. And we've converted this time into a different thing called ppm, okay? We've taken a time domain and turned it into parts per million. And we basically just spread that out over a certain amount of space. And that's what we call position, okay? The last thing we want to deal with is what we call spin-spin signal splitting, okay? So let's say I have a molecule, and on this molecule, I have 2 hydrogens over here, and they are equal to each other. And these 2 hydrogens over here, and they are equal to each other, but these 2 sets are not equal. They can see each other through up to 3 bonds, and they will start to split the other signal because they're not the same. If they are the same, you get 1 signal. If they're not the same, you start splitting the signals based on how many hydrogens you have. Okay, so I'm going to go through each of these things one by one and show you their importance and where we're going to find them. Okay, so the other thing you can think about is that the 4 things we have to remember are spin. Read it in this direction here, it's S-P-I-N. So you'll know all 4 things: spin, position, intensity, and number of signals. Okay, but I'm going to go through them in the other way. So if we look at a standard NMR spectrum, what we're going to see is we're going to see a nice little graph, and we're going to have a graph of intensity on the y-axis right here. And then we're going to have this right here. This is ppm, okay? And ppm is what we call the chemical shift, okay? Now, these are all done in a kind of a weird coordinate system where 0 always starts on the right side of the signal, and it goes up. And for most proton NMR, Most of the signals are found between 0 and 10, except for some things. Some things will go up to maybe 15. Okay, so that's the shift of the different things possible for us. Okay, so this is shift. Now, what we're looking for right now is number of peaks. Okay, so number of peaks tells us how many different types of hydrogen you have. So let's look at this compound right here. So you're saying, oh, well, these are all sp3 hybridized carbons. And so that makes them sp3 hybridized hydrogens, right? So they're all the same, right? Well, no, because we are looking at things through at least 3 bonds. And so we have, if we drew our hydrogen out here, this hydrogen sees a carbon, but then it sees a carbon, and then eventually it sees a bromine, okay? And if we draw this hydrogen here and this hydrogen here, and we drew that same line, all 3 of these hydrogens are the same because they all are connected the exact same way, okay? So what about these next hydrogens? Well, if we look at this hydrogen here, it's bromine in this direction and a carbon that direction. That means this hydrogen is not equivalent to that hydrogen. And if they're not equivalent, that means we have a separate peak. Okay. So equivalent has to do with what's attached, what's its closest neighbors. Okay. And if we do this hydrogen down here and we do the same thing, it's going to be identical to this one. So those 2 are the same type of hydrogen. And these 3 are the same type of hydrogen. But we have 2 different types of hydrogen, so we should have 2 signals. 1 signal for this one and 1 signal for this one. So we should have a total of 2 signals. Okay, so that's number of signals. It's non-equivalent hydrogens. Okay. So how do we recognize non-equivalent hydrogens? Okay, well, we look at our structure and we decide what equivalent hydrogens are and what equivalent hydrogens aren't. Okay, so let's look at this compound right here. And what I would like to do on at least just this one here is I want to draw all 3 hydrogens on this methyl group, but I also want to draw this hydrogen here, okay? Now, if we look at these hydrogens here, oops, these hydrogens here, right? Okay, so it's 3 hydrogens and they're connected to a carbon, which connected to a carbon with 1 hydrogen and then, right? But the hydrogens here see the exact same thing that these hydrogens do. And the hydrogens here see the exact same these hydrogens do. So what that means is all 9 of these hydrogens are the same type of hydrogen. So that gives us 1 set of hydrogens for there. Now this hydrogen does not have 2 other hydrogens next to it, so it's automatically a different hydrogen. So that makes this a different type of hydrogen. So this would be our second peak we see. Okay. So you see the difference between equivalent and non-equivalent hydrogen. Okay. It's kind of through space. And remember, these are all equal also because we have free rotation around this bond. So it's not like one of those hydrogens is closer to the other hydrogen. We have free rotation. And so all 9 of those hydrogens are identical in space. Okay.
Professor Irving?
Yes.
So whenever it came down to it, you labeled them 1 and 2 just so you knew there's different ones. When it comes down to it, do we need to have a specific name for the hydrogen or do we just need to recognize differences?
We will, so if you were going to do it in a spectrum, you just label them A, B, and C and show where they are.
Okay.
Yeah. So, and it'll be obvious a lot of times because remember, one of the things that shows us its intensity. And so if we look at one of your peaks is going to have a value of 9 and one of them is going to have a value of 1. And so you're going to be able to tell the difference that way too.
Okay. I appreciate that.
But this one, all we're talking about is what they look like in space. Are they different or are they the same?
Yes, sir.
Okay. So let's do that same analysis on this next one over here. So I think this methyl group right here is the same as this methyl group right here, but it's different than this and it's different than that. Notice it's different than this because both of these methyl groups have that methyl group adjacent to it. This one does not. This one has 2 hydrogens here. That's making this methyl group not the same as these, okay? Because the connections are different, okay? So that makes this methyl group separate. So we have, this is, let's call these hydrogens A. We see why those are equivalent, because if we look at the connection here, 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 they're identical, okay? So that being said, we have our A group now. And now, because this methyl group here is different, we're going to call that our B group, because those are different than everything else. That's our only other methyl group with 3 hydrogens on it. So we think all 3 of those hydrogens are the same. But let's not forget that we have a hydrogen here, and a hydrogen here, and a hydrogen here. Now, the fact that one of those carbons has 1 hydrogen and one of those carbons has 2 hydrogens means they're not equivalent. And so now we have 2 more types of hydrogen. So we're going to call this hydrogen just C. And we're going to call this hydrogen over here D. Okay. Now, that's how we find equivalency. Okay. So if these are equivalent, how many hydrogens do we have in each set? So just for these methyls right here, how many hydrogens do we have on those that are equivalent in that set? Right, we have 6 equivalent hydrogens because each of these has 3 and they're equivalent. So we're going to say A has 6. So when we look for the intensity or the area under the curve, and I'll show you what that looks like in a minute, we're looking for 6 hydrogens. So that means B is going to have how many hydrogens? We only have that 1 methyl group, so that's probably going to be just the 3, right? And when we go to our peak C now, we only had 1 hydrogen there, so we're going to look for 1. And peak D had 2 hydrogens, so we're going to look for 2. So that's how we find equivalency and how many hydrogens that are equivalent. And so now from this idea, we're going to have a total of 4 peaks, A, B, C, and D, and they're each going to have a different number of hydrogens. And so we should see the difference when we look at the intensity of the peak as well. Now let's do a hard one. Ha ha ha. We just learned benzene, so let's go ahead and look at this. So the benzene ring itself, because it doesn't have free rotation, we might have some differences here now. So let's do the easy one first. Let's do this methyl group here and this methyl group here. If we look at the connections, they have the same connections going either way. So I'm going to say that those 2 methyl groups are the same. And we're going to have a total of 6 hydrogens for those 2 methyl groups. But let's look at the ring. Okay. So this one's special because it only has that 1 hydrogen and it's between 2 methyl groups. So it's not like any of the other hydrogens in that benzene ring. So I think this is our second one, and it's going to have 1 hydrogen in it. Let's look at this one. This one's not like any of the others too. So it's also going to be separate, and it's going to have 1 hydrogen in it. But these 2 hydrogens, 1 on each side, are the same. Because look what it's connected to. This is connected to that, and this is connected to that. And if we continue around the ring, these are all connected the same. So that makes this D hydrogens, and there's a total of 2 of them, equivalent. So we should see 4 peaks in our NMR for each of those different types of hydrogens. Okay, do we understand equivalent versus non-equivalent hydrogen? And then let's not forget to count them all when we talk about our intensity. Okay, so that's equivalent hydrogens.
Well, I have a question.
Yes.
I have a question. So with the homework, so if it's, I just like have it open. So it would be like the number of signals is the amount of different types of hydrogens there are?
Correct.
Okay.
So equivalent hydrogens tells you, so if they're different types of hydrogens, you have a signal for each different type. Okay. So,
Gotcha.
so this is kind of misleading the title here. The number of signals comes from the number of different types of equivalent hydrogens you have.
I also have a question.
Yes.
For example B, how many does D have? I'm sorry, I missed that one.
It has 2 hydrogens on it.
2 hydrogens. Okay, that's what I was thinking. But
Yeah, when it was drawn there, it's bonded to 2 different carbons with nothing else. So we assume the last 2 connections to be hydrogen.
okay, thank you.
Okay, so the number of different sets of types of hydrogens gives you the number of signals. Now we also drew the number of hydrogen in each set, and that's going to go to our next thing, our intensity. So the intensity is a little deceptive because when we look at it, one peak might be taller than the other, but one peak might be split. And so what we're going to look for is the total area under the curve, and that's what we call the integration. And so those integrations should be equivalent to the number of hydrogen, equivalent types of hydrogen. Okay. So let's go ahead and talk about equivalent hydrogen and what the intensities would be. Right here, if we look at this simple thing, acetone. Okay, so this is our hydrogens and this is our hydrogen. Are those equal hydrogens? First of all, that's the first thing we have to decide. So I think those are equal because they are both bonded to the same thing. They both have 3 hydrogens on it and there. So that means the intensity or the area under the curve of that thing should be a total of 6 because we have a total of 6 hydrogens that are equivalent. Okay. So that was simple. All right, let's go to another one. Let's look at this here. Ooh, this one's hard. We have, let's see, a chlorine, a carbon, and then a carbon with 2 hydrogens on it. I'm gonna draw the hydrogens here. And then a chlorine, a carbon, and a chlorine. Ooh, how many types of hydrogens do we have here? Because it's symmetrical, we only have 1 type of hydrogen. So that means all 4 of those hydrogens are the same, therefore our intensity is a total of 4.
Professor Irving?
Yes.
So there's a correlation with the symmetry of it?
Yes. Symmetry
Okay.
helps with symmetrical molecules tend to make it easier to, number one, they have fewer number of peaks because they're symmetrical, and you're more likely to have equivalent hydrogens.
Okay, that makes sense.
Okay, which brings us to our last one. We have symmetry in this ring. So how many equivalent hydrogens do we have in cyclopentane?
5?
How many hydrogens are bonded to each of those carbons? This carbon has how many hydrogens on it? We bond 4 times to carbon. We have 2 carbon bonds, which makes this 2 hydrogens. So how many equivalent hydrogens do we have on the entire cyclopentane?
10.
10, exactly right. So even though it's a ring, and even though they kind of, well, what if I draw it here? What do I draw it here? No, those are all equivalent. And so we would use that in our number of intensity count, okay? So symmetry actually helps us a lot in NMR, but sometimes it can play tricks on you. So now let's go ahead and look at equivalent molecules on things that aren't symmetrical, okay? And look at how many hydrogens we would have in each one. So when we look at this right here, we see that this chlorine, this carbon right here has 1 hydrogen on it, and this carbon has 3 hydrogens on it. Immediately, those cannot be identical hydrogens because they have different things bonded to the carbon they're bonded to, meaning we now have 2 different possible signals, signal A and signal B. Okay. So whenever you have dissymmetry, you have to think that in. Remember when we did that xylene, with those different parts of the xylene had different places. Now let's go ahead here. Ooh, we have symmetry element, but it's not 100% symmetrical. We now have something breaking the 100% symmetry thing here. So that means the 2 hydrogens that are here and here are equal because they're both adjacent to the carbonyl. But these two right here are different than those because they're not adjacent to the carbonyl. Okay, there's still a symmetry element, but that makes these equivalent to these and these equivalent to these, but they're still different. We have two peaks for 4 here and 4 hydrogens here. Okay. All right, so are we starting to see equivalency, and we're starting to see number of what our intensity might be. Okay, on this one here, it's not symmetrical at all, so we got to start from one side or the other. So if we started the hydrogen on this side, it is definitely different than this one, and it's different than any of these. So this is our first signal, and it's going to give us an intensity of 1. Okay. So moving to our next hydrogen, this hydrogen is definitely not these hydrogens because it's bonded to a sp2 hybridized carbon. So we're going to have a second signal, and it's going to have an intensity of 1. And these are different than everything else, so we're going to have a third signal with an intensity of 3. And even if this was the other isomer, they're still going to be different enough that they would have different peaks. All right, so unlike the cyclopentane that we just did in the last slide, the cyclohexene here, because of that double bond, it's no longer 100% symmetrical, and now we actually end up with 3 signals. The first signal is where the alkene is. These 2 hydrogens, so we're going to have a total of 2 there for those alkene hydrogens. Then we have the things that are next to the alkene, and we have 2 hydrogens here and 2 hydrogens here for a total of 4. Then we have the thing that's farthest away from the alkene, and we're going to have 2 here and 2 here for a total of 4. So we're going to have 4, 4, 2 in these 3 different signals. Okay. You're starting to see how to break these different things apart to turn them into different types of signals. Okay. Okay. So, and we've also, when we define different types of signals, we're defining the number of hydrogens in each type of signal, because we're going to be able to use that when we read a full spectrum. Okay, so now that we know that we have different types of peaks and different intensities of peaks, we now need to talk about the shift, okay? So shift is the going from that 0 point and going down, going to higher numbers, okay? So if our definition of 0, our standard is that silicon with 3 methyl groups on it, 4 methyl groups on it as 0, we're going to call that 0. And so everything else is positive from that point on, okay? And what we're going to see is we're going to see a nice little theme associated with it. We're going to start with hydrogens that are on sp3 hybridized carbons. Then we're going to move to hydrogens on sp2 hybridized carbons. Then we're going to see things that are bonded to heteroatoms like nitrogen and oxygen. And then we're going to see things next to electron withdrawing groups, halogens, and then finally into aromatic rings. Okay. So if we look at that just in general here, we have our sp2 hybridized moving up to our sp3. Oh, that's sp2 hybridized. This is our sp hybridized right here. And then these are sp2 hybridized, but they're right next to electron-rich aromatic rings. Okay. And then once we get them next to things like oxygen that have heteroatoms, it moves them way up. And by having them next to electron withdrawing groups, it changes where they are as well. It moves them up, but not as high as electron donating groups. Then halogens right here will move us up even higher into the 3 range. These are our sp2 hybridized carbons. They're way up here at 5. So we started at 1, and just by playing around with oxygen and stuff, we get them up to around 3. But by the time we get to an sp2 hybridized carbon, we're now at 5. And then if we turn it into an aromatic ring, and we just found out aromatic rings are, you know, that have aromaticity, and that shifts it even higher, almost to 8. Then the last two outliers that are, these are the only two things that are outside that 10 range are aldehydes. That hydrogen on an aldehyde is right at 10. And then the carboxylic acid can be as high as 15, 10 to 15. Okay, so most of the time, all of our peaks we're going to see are from 0 to 10, and they kind of follow that rule. Okay, so the general idea is shielding, the closer it is to just a regular sp3 hybridized carbon, the closer it is to 0. If you add electron density, you add an oxygen or a nitrogen or a carbonyl, it's going to shift things downfield up to higher numbers. And the highest thing we look at is benzene rings are going to be the high end, aldehydes and carboxylic acids. Now, the other cool thing is that in the aldehyde and the carboxylic acid, those each only have one hydrogen. So you can really easily identify those peaks up in that range. Okay, so this is shift. So we saw number of peaks. We saw intensity of peaks, which is the number of hydrogens of each type. And now we're looking at shift, okay? So those are 3 out of 4 of the things we need to know to do read an NMR. The last thing we need to know to read an NMR is splitting, okay? So a peak is just those number and type of equivalent hydrogens, okay? Now, if they were all equal and there was nothing nearby splitting it, you would get a single peak. Okay. However, if you have non-equivalent hydrogens within 3 bonds, hydrogen to carbon, carbon to carbon, carbon to hydrogen, those hydrogens that are that third bond over can split that peak. And it's going to split it by the number of non-equivalent hydrogens. So the rule is what we call n plus 1. Okay, you get 1 peak for all of the equivalent hydrogens on the carbon of interest. Okay, and if you have only 1 hydrogen within 3 bonds, it's going to give you n plus 1. So if you have 9 hydrogens here next to 1 hydrogen, you're going to get 2 peaks for a total of 9 hydrogens. I'm sorry, a split into a doublet right there. Okay. So you get, no matter how many hydrogens are in this particular single peak here, we only count the number of hydrogens of non-equivalent hydrogens nearby. Okay. So if we had this 1 peak here and we had 2 non-equivalent hydrogens nearby, we'd have a total of 3 peaks. We'd have a triplet. If we had 1 hydrogen here and then we had a methyl group with 3 hydrogens on it, that's going to give us a total of 4 peaks. So that's what the n plus 1 means. You get 1 for the peak itself, and then plus 1 for each and every non-equivalent hydrogen nearby within 3 bonds. Okay, so what does this look like? Okay, so in the case of this compound here, let's predict what we're going to see. Okay, so we already figured out that these hydrogens right here are different than these hydrogens, so we're going to have 2 peaks. Okay, and we figured out we had, so if this is peak A, right here, we're going to have a total of 2 hydrogens in that peak, so that gives us our intensity. Okay, and B has 1 hydrogen on it, 1 hydrogen on it, so that's going to give us our intensity. Okay, but now how does that help us with splitting? Okay, so both of these hydrogens right here are going to give us 1 peak. Okay, and this hydrogen right here is within 3 bonds of these hydrogens over here. So this hydrogen splits this peak 1 hydrogen because it has 1 hydrogen. So that means we're going to have a total of 2 peaks for peak A. 1 for the hydrogens that are equivalent, 1 for the hydrogen that's within 3 bonds. Okay. So if that's peak A, let's do peak B. Oops. So let's look at peak B. We already said peak B had 1 hydrogen on it, so we get 1 peak for that. but we have 2 hydrogens within 3 bonds. So we have our 1 plus the number of hydrogens nearby. So we're going to end up with a total of 3 peaks or a triplet. So this is going to be B. Do we see why we have this splitting pattern? Okay. We get the equivalent hydrogens give us our peak.
Is that the same as like multiplicity? Is the amount of peaks there are?
Correct. The multiplicity is what we can say like, so a single peak is a singlet, a double peak is a doublet, and then we have triplet, quartet, pentet, etc. That's what we call multiplicity.
Okay, thank you.
And so if you take, let's say your peak was split into 7 peaks, okay? That means that you had your regular peak here, plus there were 6 hydrogens somewhere nearby that split that peak. N is the high number of hydrogens nearby, yes. So if you had a multiplicity of 7, that means that you had 6 hydrogens nearby. And they can be equal or not equal, it doesn't matter. It's because they're nearby, they each split. Now, that's why here, notice that when we had these right here, it split this one once. I'm sorry. This peak right here was split just once because we only had 1 hydrogen. So that's the N, 1 hydrogen plus 1. So we had 1 plus 1 equals 2. Then we had these over here, which were 1 peak there, and they were splitting this 1 hydrogen here. And so we had our single peak, which is our 1 for this hydrogen here, plus 2 other hydrogens for 1, 2, to give us a total of our 3 peaks. Okay. All right. So if that's what we predict the spectrum to look like, let's go ahead and actually look at the full spectrum. So the first thing I want to draw your attention to is this is what full spectrums look like, okay? It starts way down here at 0. And notice there's usually a little peak here at 0. And the reason there's a little peak here at 0 is because we usually put a little bit of that so we know where 0 is, okay? So everything's measured off that peak. And then you'll might notice that there's a little kind of little fuzzy bits in here. This and this and this. These are probably solvent or impurity or water or something like that. But we know that our other thing is the more important thing because it's the biggest peaks, okay? So we know that there are 2 peaks total there. 1, and if we look at this is what we call our integration. Integration is just basically totaling the area underneath that curve, and that gives us an accurate representation of intensity. You can't just add up the heights of all these peaks because they all have different widths. So we actually look at the total area underneath them, and that gives us what we call our intensity. And in this case, here we've integrated our intensity to be 1 hydrogen, and we've integrated this intensity to be 2 hydrogens. Now, that being said, we now know exactly which is A and which is B on our structure because the number of hydrogens, okay? So that's one thing we can look at. Now let's look at what we expected to see. We expected to have a triplet. And if we blow that up there, we have 1 peak in the middle and 2 on the sides. So we have our triplet. Okay. And if we look at this one, we blow this up at the top, it looks like a doublet. And if we blow it up at the bottom, it just looks like, yeah, doublet again. So it's showing us that this is the classical splitting pattern. Now, what else does it show us? Okay. The B right here is the carbon, chlorine, chlorine, hydrogen. And it's this hydrogen is our B. Okay. This hydrogen right here, this is our chlorine, chlorine, carbon, hydrogen, hydrogen, carbon. Okay. Let's look at the shift. Okay. Oh, where did you go? Now let's look at our shift, okay? So if this one over here was a carbon with a chlorine on it, and this is the hydrogen here, we have two halogens on there. So that's going to deshield it, move it farther up than the one with just one chlorine on it. See, this one has two hydrogens, one chlorine, and then a carbon attached to it. So this chlorine right here is shifting it up from 1 to here, but the fact that we have two chlorines on this one shifted it even higher. Okay, so we have two things telling us which hydrogens are which. We have shift, and our shift agrees with our splitting. So we have splitting, shift, and intensity all agreeing to the way the structure is drawn. Okay, so that's great. So all of our things, our number of peaks is correct. Our shift looks consistent within the set, you know, one chlorine versus two chlorines. Our intensity looks correct, and our splitting looks correct. So when we look at our NMR, we want to have all four pieces of information agree. Okay. So let's talk about splitting it a little bit more and kind of work through that n+1 thing again. Okay. Oh, trying to get away from me. Okay. So let's look at this molecule here. Okay. So first of all, if we were to predict in order where things would be, which of these carbons, 1, 2, or 3, would be closest to 0? Just based on what's attached to it. In shift, right. This one is the closest we have to just methane right here. So this is probably going to be the furthest or lowest number. So it's going to be the one closest to 1 ppm. That's just its shift location, right? So if that's true, this is going to be the one that's highest up. So because of this electron drawing group here. So that's going to put number 2 in the middle. So if we look from, 0 up, we're going to see 1, 2, and 3. So that's shift assigned just based on what's attached. Okay. So let's assign then also our intensity. So we have shift and, well, okay, let's assign number of peaks though. How many different types of peaks do we have? So the fact that I labeled them 1, 2, and 3 might make you think, oh, well, we only have 3 signals. Well, let's look at it. These 3 hydrogens are different than everything else because it's 3 hydrogens. It's the only set of 3 hydrogens. It's different. These hydrogens are different than these hydrogens because of the chlorine. So yes, it turns out we do have 3 signals because we have 3 types of hydrogen. We now know the order in which they're going to be shifted. And now that we have all the hydrogens drawn, we can also do intensity. We're going to have a 3. Our intensity is going to be 3, 1, 2, 2. But now we need to do splitting. Okay. So we have shift, we have number of peaks, and we have intensity. Now let's do splitting. Okay. All right. So if we predict the splitting on this, let's do carbon number 1 first. Okay. So all of these hydrogens are the same. So that's our 1. Now, how many hydrogens are within 3 bonds of these hydrogens on carbon number 1? Okay, we have 1, 2, and then that's a carbon, so there's no more. So we have a total of 2 hydrogens that are next to the peak here with this one. So we have our N is equal to 2, so we have 2 plus 1. So we expect our carbon number 1 to have 3 peaks, or a triplet. Okay. Now let's go do number 3 because it's going to be easier. Number 3 here. Okay. So if we look at how many hydrogens are within 3 bonds, 1, 2. So we have a total of 2 there, which if we do our 2 plus our 1 is equal to 3. So that means peak 3 is going to have 3 peaks. And so we're going to look for a triplet down there. Okay. And now let's do peak 2. Okay, let's do 2 in, I should have done this one in blue. 3 and a triplet. Here. Now let's do the last one. Okay, so if we're looking at this one, we have 1, 2, 3, 4, 5. 5 hydrogens within 3 bonds, which means that our peak 2 here is going to have 5 plus 1 is equal to 6. So it's going to have a sextet, 6 peaks on it. So here we should see, so now we've predicted our Nmr spectrum just by looking at those few things, right? We know which is going to be shifted most upfield and which is most downfield. We know how many hydrogens we should see in the integration or the intensity. We know how many equivalent and non-equivalent steps we have, so we know what the splitting should be on each and everything. So we've identified different types, intensity, shift, and multiplicity, or spin-spin coupling, So let's go look and see if we're right, okay? So now we've applied all of the rules of spin coupling, position, intensity, and number of peaks. And okay, well, there's nothing way up here. Well, we wouldn't expect to see anything up here because those are all sp3 hybridized carbons. So let's keep going down the field here. Not seeing anything there yet. Oh, okay, we got our first peak. Okay, so in looking at our answer here, we again have our 0 peak right here. And we have 3 peaks, okay? We have peak 1, peak 2, peak 3. We have peak 1 has 3 hydrogens, peak 2 has 2 hydrogens, peak 3 has 2 hydrogens, which is what we expected. And we expected that peak 1 and 3 to have triplets, okay? So peak 3 here has a triplet, peak 1 here has a triplet, and we predicted the middle peak, peak number 2, to have 6 peaks. So let's blow that up. And I count 1, 2, 3, 4, 5, 6. So we were able to predict the peaks. We were able to predict the shifts. We were able to predict the number of hydrogens. We were able to predict the splitting. Okay? So that is what we can be able to do. Any structure, you can compare and contrast and try to shift them up higher. So let's talk a little bit more about predicting splitting patterns, because what you're going to see is that the first couple times it's going to be hard. You got to start thinking about different little things, but then after a while it starts to get really, you start recognizing patterns. Okay, so let's start talking about recognizing patterns. So let's start with this first one. So the first thing you should recognize is how many types of hydrogens you have. Okay, so just at first blush, these hydrogens are not like those, so we have a total of 3 types of hydrogen. Okay, now the second thing we should note is that these are going to be the furthest downfield because they're the most like just a methane. These 2 are going to be next to it because they have something other attached. In this case, it's a carbonyl. So now we knew a little bit about shift. And we know about our intensities are going to be 3, 2, 3 because of our hydrogens. So now let's do our last and hardest one, splitting. Okay. So in splitting, if we look at this first one here, there are no hydrogens. I'm going to draw one of the hydrogens here within 3 bonds. Therefore, this is going to be a single peak. Okay, so we're going to start to recognize that pattern. If there's something in between, like if there's an O C, and you have 3 hydrogens out here, that's going to be a single peak because there's no hydrogen. So we're looking for those things that are separated that don't have hydrogens within 3 bonds. And those are always singles, okay? So that's going to be a pattern we'll recognize, okay? So that means we're going to have a singlet, and I'm going to do it as an S here. Singlet. Okay. Now we have another fragment that's very common. We have a CH2CH3, okay? So empirically, we know they're different because of the things that are attached to the side. However, we also should be able to come up with a predicted pattern for this particular fragment, okay? And if we think about it, this is our N+1, and this is our N+1, right? And there are 3 hydrogens over here, and there are 2 hydrogens over here, meaning that our N, so this is going to give us a quartet right here, and this is 2 and 1, so this is going to give us a triplet. So anytime you see an ethyl group off by itself, we're going to see the classical pattern of triplet, quartet. This is your standard ethyl pattern. Your methyl by itself is always a single. So we should start to see that adding those, doing a few of these examples in the homework, you should start seeing a pattern arise. Okay, now let's do this one. Now we have to think a couple other things. How many different types of hydrogens do we have here? Type your answer. How many different types of hydrogens do we have here? Looks like it could have, well, it definitely has more than 1. Be sure for that. Could have up to 4. But symmetry makes me think there are 2 types of hydrogens here. Okay, so there's this type of hydrogen and this type of hydrogen. Okay, so that's going to tell us something about intensity, right? Now, the other thing is that this is that same methyl ethyl group separated by something, and then an ethyl group separated by something. So we should expect to see the exact same pattern. We should see the triplet and then the quartet. Right there. And notice the quartet is shifted higher upfield because it's closer to the group that's not like the alkane. So symmetry helps us there, but when we do our integration, we're going to have 4 and 6. So that's the only difference between the methyl group on the ethyl group over here and the ethyl group here, is that integration under the curve. All right, so now let's put you to the test. Okay. Now, whenever you see something like this and you're trying to predict your number, draw it out again, because what we're not seeing, we might miss something. So what I want to do is I want to redraw it. And this methyl group is off by itself, so I don't have to redraw that one. But we have a hydrogen and a CH3 and a CH3. Okay. You can have them on the same side, it doesn't matter. But what I wanted you to see is that if you redraw this, you start to see your different groups now. Okay. So we have one group here, and it's off by itself. And so it's a singlet. Okay. These 2 groups are equivalent because they have the same connection. Okay. So we have a total of our N is equal to 6 here. Okay. And then that leaves us our last one here. Our last one there, that's our N is equal to 1 because it has 1 peak there. So if this was a singlet because they're off by themselves, let's talk about this hydrogen here. Okay. So we get 1 peak for the hydrogen itself, and the N associated with that is the number 6. So this right here is going to be a septet, or a heptet, sorry, 7 peaks. This hydrogen is going to have 7 peaks because of these 6. But how many peaks are these going to have? how many peaks do those 6 methyl groups, those 6 methyl hydrogens have? It's going to give us a total of 2 peaks because remember, these are all equivalent. So that's our 1 plus our N next to it is 1. So we're going to get a doublet. So our peak here is going to be something like a singlet way down here because it's most out here. Then we're going to get a 7. And then we're going to get a doublet. So that's what we can predict our species to be, following all 4 of those rules of how many, number of peaks, intensity of peaks, shift of peaks, and splitting pattern. All right, questions on splitting. Splitting is probably the hardest part of this. The next hardest part is probably figuring out where shifts are. And the thing you want to look about it is the closer it is to just methane, the closer it's going to be to 0. Anytime you have anything else, it's going to start to shift down. And the general trend for shifting down is things like oxygen are going to shift you up in the 3s. Carbonyls are going to shift you in the 2s. Double bonds are going to shift you into the 5s. And aromatic rings are going to shift up into the 7s and 8s. Okay, so if you can just kind of follow those general trends, you will see that that goes from most like sp3 hybridized hydrogen, which is the least shielded, up to a benzene ring, which has a whole bunch of electron density on both sides of it. So think about that's why it's so high up. Okay, so that is what I'd like you to know about proton NMR. Any questions?
Professor Irving.
Yes.
So this little chart right here, we should probably get pretty familiar with it. So whenever we do see those little elements, not elements, but those in particular ones pop up, that'll be like a giveaway.
Yes, and in the book, let me see, where do I have a copy of the book? They actually have another thing. I think it's a simpler chart than this even. They kind of give you a relative, or did I use their chart? There's a visualization. Oh, it's not in this book. It's in the other book, sorry. Yeah, so but you can look at the general trend by just, okay, how close is it to an sp3 hybridized hydrogen? Is it going to be closer to 0? So usually if there's, and if you add like 2 chlorines, it's going to shift it even higher than 1 chlorine. So you can really rationalize it out thinking of, where would an oxygen be? Oh, around 3. So are there 2 oxygens? It's going to be shifted higher or lower.
Okay, yeah, that makes sense.
So like, for example, when we talk about this right here, the ester, that's 2 oxygens. Therefore, it's higher than the 3. It's now, right. And just like the 2 chlorines was shifted all the way up to 4.
So just 100% kind of knowing where their base, I guess, chemical shift density is, and then just realizing, oh, there's 2 of them, 3 of them, cool, it's going to be over here.
Right. So, the shift is not 100% additive, but definitely predictive. So,
yes, sir.
Like right here, we know that, notice this is shifted at 5.5 because it has 2 chlorines on it, where just 1 chlorine is 4.
Okay.
So
appreciate that.
We can tell the difference. And sometimes you can also just tell the difference by the number of protons. So,
yes,
but don't get tricked saying, oh, it's got to be shifted more, but the integration's backwards. If the integration's backwards, you got to do all 4 things: number of peaks, the splitting, the shift, and the integration. If all 4 things agree, you have the right structure.
Just the roadmap to kind of figure it out.
Right. Don't take any one thing over another. They all have to match.
Yes, sir.
Okay, a quick question on splitting. All right. Let me go with this green space here. Okay, for example, drawing in this structure here, okay. What is the, oops. What is the splitting of A and what is the splitting of B? So for example, if you're looking at that going, okay, first thing you always do is you either write down or imagine where the hydrogens are, okay? So in this case here, we're gonna have a hydrogen here and a hydrogen here. In this case here, we're gonna have a hydrogen here and a hydrogen here, okay? So because there's a chlorine here and because there's this here, they're non-equivalent. So we're gonna have two different peaks. And now that we have two different peaks, we have two different shifts because this chlorine is gonna shift it up higher. So you're gonna say, okay, so let's look at our splitting, okay? So we had our 1 for our peaks here, and then we have 2 hydrogens next to it. So we're gonna have a triplet. And then let's look at our splitting for B here. Our B, these are equivalent, and we have 2 hydrogens nearby, so it's 1 plus 2. So that's gonna be a triplet. And A is gonna be further upfield, and B is gonna be closer to 0. So just given the structure, you can tell number of peaks, multiplicity or spin, spin-spin coupling, and where their general place would be in the spectrum. Okay? So let's try another one. I have a really weird one that I think causes trouble sometimes, but I want to do it. Okay. Okay. So this one here. Okay. So we have we have 4 types of hydrogens. Okay. So we have group 1. They're all the same, and there's a singlet because there's no hydrogens anywhere nearby. Okay. So I'm going to draw the hydrogens that we are worried about. Okay. Now, this group over here, that's isolated. That's going to be a singlet, 3 hydrogens. So this is going to be a singlet with 9 hydrogens. This is going to be a singlet with 3 hydrogens. So we have to deal with the last 2 peaks here. Okay. So the last 2 peaks are, we have, let's do this one right here. We have those 3 hydrogens are all equivalent and they're being split by 1 hydrogen. So we're going to have 3 hydrogens as a doublet. Doublet, or 2 peaks. Now let's look at our last thing here. Our hydrogen here. We're going to have 1 hydrogen split 1, 2, 3 times. So we're going to have with a quartet. Okay. 3 types of hydrogens, 2 types of splittings, 3 different intensities, all in the same molecule. And you could predict the shift being that these are going to be the closest to 0, next closest to 0, farthest away from these, and then this is going to be the highest up because it's bonded directly to an oxygen. And then you double check, checking your integration to make sure you're right. Okay? So if you want to hang back and ask a couple more questions, go ahead. Otherwise, I'm going to stop recording, and anybody who needs to run off to class, you may. And if you want to hang out and ask questions, please do stop.